Let's just dive right into this explainer, because today we're going to completely shatter the everyday assumption that the buildings we live and work in are just safe, static boxes. I mean, think about it. When you walk into a room, you naturally expect the floor to hold you up, right? You expect the walls to stand firm. It's actually kind of funny how much blind faith we put into some drywall, concrete, and a few wooden studs to keep the absolute wrath of Mother Nature at bay. We totally take for granted that architecture is this permanent sanctuary from the outside world. But what happens when the very physics of our planet decide to test those assumptions? Today, we're unpacking the deep science of structural failure. We're looking at exactly what goes down when our built environment faces the unapologetic absolute extremes of the physical world. Because sometimes it literally feels like nature holds a personal grudge against civil engineers. Imagine the sheer terror of a massive earthquake, or even the unimaginable force of a nuclear blast. In those extreme moments, the ground doesn't just shake back and forth like some crazy carnival ride. Nope. Through a terrifying physical process called liquefaction, the very earth beneath you literally stops being solid and turns into a liquid. For geophysicists, the mechanics here are both fascinating and entirely terrifying. When the ground violently shakes, all that intense kinetic energy basically squeezes the groundwater trapped deep down in the soil. The water pressure spikes so fast and so hard that it forcefully pushes the dirt particles apart, completely breaking their structural contact. So what was solid ground a second ago functionally turns into flowing, quicksand-like fluid. If your building is just sitting perfectly still on a traditional foundation when that underlying physics shifts, man, it doesn't matter how strong your walls are. The whole structure just sinks, folds, and catastrophically fails.
So, in that high-stakes scenario where the Earth is literally liquefying beneath a colossal structure, just pouring more stubborn concrete is totally useless. Your only real hope for survival comes down to an engineering marvel called base isolation. Picture an entire building resting on a network of 1,000 massive engineered shock absorbers. These isolators are usually these incredibly dense sandwiches made of thick rubber, steel plates, and solid lead cores. By physically decoupling the base of the building from the chaotic, shaking ground below, these giant springs do something practically magical. Instead of fighting that immense kinetic energy with stubborn rigidity, the building dynamically absorbs it. It actually floats above the chaos. It rides the wave of destruction instead of trying to stand perfectly still against it.
Which brings us to Section 1, the illusion of shelter, rethinking our static boxes.
Moving right along to Section 2, engineering for Armageddon, surviving the unsurvivable.
Surviving the unsurvivable means we have to completely abandon everything we think we know about everyday construction. We have to design for the absolute worst-case scenarios that planet Earth, or human conflict, can possibly throw at us. To really wrap your head around this jaw-dropping scale of engineering, let's look at the Cheyenne Mountain complex. To survive a direct nuclear hit, they don't just build thicker walls. No, they use massive blast doors that weigh an astonishing 25 tons. Just think about the sheer mechanical force needed to move a 25-ton door on a daily basis. They rely on these massive industrial hydraulic systems just to swing the things open. And when they close, they aren't just shutting a room. They're forming an absolutely impenetrable seal against the devastating overpressure of a nuclear shockwave. It is a staggering testament to what it actually takes to keep a structure intact when the environment outside is literally exploded.
And this highlights a really crucial architectural paradigm shift. Your everyday standard buildings, they rely entirely on rigid foundations. They're designed to stand perfectly still and bear weight vertically, transferring all that gravity straight down into the dirt. But here's the catch. Rigidity is a building's absolute worst enemy in a blast or a major earthquake. Kinetic energy from a shockwave always demands somewhere to go. If a rigid building refuses to bend, it's going to break, period. Extreme structures, like the Cheyenne Mountain complex, survive because they abandon that rigidity entirely. By using those massive base isolation springs we talked about, they yield, they move, they absorb all that devastating kinetic energy right into their framework. By rolling with the punches rather than fighting the force head-on, they survive the unsurvivable.
And that brings us to Section 3, when nature fights back. Amplified elements.
So we've talked about the Earth moving and massive impact blasts from the ground up, right? But now we need to look upward. We need to see what happens when the atmosphere, the weather, and gravity go on the offensive. Because when nature fights back, it actually uses the laws of thermodynamics to amplify the elements against our structures. Take the snowball effect, for example. Now, this isn't just some casual figure of speech for a bad day getting worse. It's a terrifying mechanical reality for any structure built in a mountainous region. You see, an avalanche doesn't just casually push against a building with the static weight of fluffy snow. It relies on the physics of mass times velocity. As an avalanche rushes down a mountain, the faster it moves, the more mass it collects and compacts. By the time it hits the valley floor, it's not even snow anymore. It's practically a flowing wall of concrete traveling at highway speeds, compounding the structural destruction exponentially until it slams into a building like a massive, calculated, kinetic bomb.
But these amplified elements don't stop with crushing weight. They can actually alter atmospheric chemistry itself. Let's walk through this totally wild story of cascading, counterintuitive failures. Imagine a severe, record-breaking cold wave hits a major city. As the temperature plummets way below freezing, basic thermodynamics kicks in, and the air molecules pack tightly together. The air actually becomes significantly denser. And because it's denser, any given cubic foot of that freezing air suddenly packs in a much higher concentration of oxygen. Which brings us to a terrifying, highly volatile reality. If a structural fire breaks out during this deep freeze, it's suddenly being fed by a naturally supercharged oxygen supply. The fire breathes like it's been hooked up to a massive industrial ventilator. It'll burn with this terrifying, amplified intensity that standard municipal fire systems just aren't built to handle. So, counterintuitively, the bitter cold doesn't suppress the fire, it absolutely supercharges it.
Let's move into Section 4, the ultimate mechanical shield, surviving a Type 1 planet.
Okay, now that we've demystified these intense physical threats, from liquefying Earth under immense pressure to supercharged cold weather fires fueled by dense oxygen, we really need to pull back for the grand philosophical takeaway of this whole explainer. It all boils down to this. We have to reframe architecture. It's not just a simple shelter, it is a dynamic mechanical shield that has to combat the physics of a Type 1 planet. To really get the gravity of that, think about the Kardashev scale. A Type 1 planet is all about immense planetary energy scales, harnessing and dealing with the full, unfettered wrath of a planet's geological and meteorological power. We absolutely have to stop thinking of our structures as passive shelters. That mindset, totally obsolete. A building is an active piece of armor. Every steel beam, every giant shock-absorbing spring, and every 25-ton blast door is a carefully calculated weapon in a constant, silent war against gravity, thermodynamics, and extreme planetary geology.
So as you look around at the walls surrounding you right now, I want to leave you with one final, mind-shifting question to ponder long after this explainer ends. Think about the invisible forces constantly pressing against the foundation beneath your feet, and the heavy roof suspended over your head. Knowing what you know now about the aggressive, unforgiving physics of our planet, is your home just a shelter, or is it a shield?